Next we have number 4, where we have to prove that for any non-negative integer n, the box value of n divided by 2 minus the box value of minus n divided by 2 is equal to n. We divide the solution into two cases depending on whether n is even or odd. Let's see the even case first. So here n is 2k for some non-negative integer k. K is non-negative because n itself is non-negative. Then we consider this left hand side. So n divided by 2 is k now. So this becomes k and this becomes minus k. Because k and minus k are both integers, so their box values are themselves. So that way we get k minus of minus k, which is 2k, which is equal to n. So in this case we are really getting this. And in the second case n is odd. So it has the form 2k plus 1 for some non-negative integer k. Here also k is non-negative like the last case because n itself is non-negative. And then again we consider this difference. This time however n divided by 2 is k plus 1 divided by 2. So minus of n over 2 is minus k minus 1 over 2. Now this greatest integer value is k, whereas the greatest integer value of minus k minus 1 over 2 is minus k minus 1. So that way you get 2k plus 1 again, which is just n. But we need a little more explanation on how we are getting these things. You look at these diagrams. Both of them are diagrams of the numbered line. In this first one, we have located k plus 1 divided by 2 as the middle point of k and k plus 1. So from this diagram, what can you say about this box value? By definition, this box value is the greatest integer less than or equal to k plus 1 over 2, which of course is k, the next integer which is to its left. That's how we are getting k here. And in this second one, we have located minus k minus 1 over 2 as the middle point of minus k minus 1 and minus k. So just like this one is k, this one is minus k minus 1, let's see. Let's see number 6 next. If n is a positive integer and p is a prime, we have to prove the following. There are three parts. This is the first one. 2n factorial divided by the square of n factorial is an even integer. We start the solution by expanding the 2n factorial in the numerator. So if you do the expansion, we don't do it fully, we stop at some stage. Let's see what that means. So you would go like this, 2n times 2n minus 1 times 2n minus 2, and the smaller integers come. How far will you go? You can go all the way up to 1 if you want. However, that is not our aim. We stop here at n plus 1, and then we should write here n factorial, because the product of these integers and n factorial is 2n factorial. But after cancelling that n factorial with one n factorial in the denominator, you have n factorial here. And then there is one more cancellation that you can do. You can cancel this n and another n that you have here, making the denominator n minus 1 factorial, and 2 has been kept outside. You understand why? Because we want to show that this is an even integer. Now if we can somehow show that this is an integer, then we are done. Luckily, we don't have to do anything extra for this. Since by the corollary to theorem 610, this part is an integer, so we are done. That means this is an even integer. The statement of that corollary is this: a product of any r consecutive integers is divisible by r factorial. We do have a product of consecutive integers here in the numerator, and the denominator is n minus 1 factorial. The question now is, how many integers there are in this product. If it is n minus 1, then by that corollary there will be divisibility, and so this will be an integer. Let's count the number of numbers here. This is the first one. If we start counting from this and go to the left, then this is the first one, which is indicated by this number 1 attached to n. The next one is n plus 2. That plus 2, that number 2 indicates that we have counted 2 factors. The next one is n plus 3. Like that, if you are going, what is this number? N plus what? N plus n minus 1. So really there are n minus 1 factors here. So that's why this is really an integer by that corollary, and so this is the solution to part A. Part B next, where we have to prove this. The exponent of the highest power of that prime p, which divides this number, this 2n factorial divided by n factorial square, is this. Summation k varying from 1 to infinity of the greatest integer value of 2n divided by p to the power k minus 2 times the greatest integer value of n divided by p to the power k. And the solution is just this one line. It's evident from theorem 6.9. Having come this far, you should be able to understand why. You go back to theorem 6.9 and see what it says about highest exponents of primes which divide a factorial. I will just, however, point one thing. This 2 here comes because you have a square here. I won't say anything more. Let's now see part C. Part C next. In the prime factorization of that same number, the exponent of any prime p such that p lies between n and 2n in this manner, n is less than p and p is less than 2n, is 1, is equal to 1. Which means that if you find a prime p satisfying these inequalities, then that prime will appear in the prime factorization of this number as just itself, as p, no p squared, no p cube, just p. We start the solution with these inequalities. N is less than p and p is less than 2n, which give us these further inequalities. I mean, the given ones are also a part of it, but we get this extra. 2n is also less than 2p, which you get from the first inequality by multiplying on both sides by 2. Okay. And then we further get these things. If you divide the first inequality by p, because everything involved here is a positive integer, so division or multiplication, these things can be done, and not just that, the inequalities do not get flipped, they maintain their direction. So dividing both sides by p, we get n divided by p less than 1, and needless to say, this is positive. That means this is greater than 0, which I did not write because it's evident. And next what we do, we divide these last two inequalities on both sides, means throughout, by p, obtaining these inequalities. 1 less than 2n divided by p less than 2. Alright. And then we further get more inequalities from these. Because n divided by p is less than 1, if you do more division by p, that is n divided by p to the power k, where k is any positive integer, then they will also be less than 1. In fact, they are even smaller. N divided by p squared is smaller than n divided by p. So obviously all of them are going to be less than 1 for all k greater than or equal to 1. Okay, and we get something similar from these other inequalities as well. Note that if you divide this last inequality, 2n divided by p less than 2, by more p's, then you get this. I mean, if you divide this existing ratio by p to the power k minus 1, okay, where this time k is greater than or equal to 2, then obviously you are also going to divide 2 by p to the power k minus 1, which itself is less than 2 divided by p, less than or equal to actually. So that's how 2n divided by p divided by p to the power k minus 1, which is this, becomes less than 2 divided by p. And 2 divided by p is less than or equal to 1 because p is at least 2. The smallest prime is 2. This p may be 2, it may be greater than 2, but in any case it will be less than or equal to 1. So you see that just like these ratios are all less than 1, these ratios are also all less than 1. See the strict inequality here. And because of these things, these greatest integer values will be equal to 0. Because they are not just less than 1, greater than 0 also. So the greatest integer less than or equal to any one of them is the first integer that you encounter when you start moving left from this integer, and that is 0. So that's why you are having 0 here for all k greater than or equal to 1. From these inequalities, you get this, which is slightly different. The greatest integer value of 2n divided by p is the first integer to the left, which is 1. So that's why this is 1. However, from these inequalities, actually we just have to consider 1 here, which is 2n divided by p to the power k less than 1, that inequality. Just like these ones give us this, these ones give us this. For all k greater than or equal to 2, do not forget this condition. So by part B, so now we have to use part B here. The exponent of p in the factorization of this is of course this, because that's what part B says. However, we are now ready to substitute these values. We know all of them. We know all the terms here. In this series, k goes from 1 to infinity. If k is equal to 1, what do you get here? The greatest integer value of 2n divided by p, which is 1. Because of that, you are getting a 1 here. What about the higher values of k? For k greater than or equal to 2, these other terms are all 0. So they vanish. And these terms are all 0 for all k. So they also vanish and you are left with only 1. And this is what you wanted to show. So here the solution ends.